Hello, I'm Minchell. I'm going to talk about RCIK, real-time collision-free inverse kinematics using collision cost prediction network. Our goal is real-time collision-free inverse kinematics in environments including dynamic obstacles. Therefore, our method targets to synthesize collision-free joint configurations for consecutively given 6 DOF commands. To solve the real-time problem, reducing the computational overhead is a critical issue. To do that, we propose two approaches. The first one is we generate IK candidates with high feasibility based on an optimization-based IK, which is very fast. The last one is we use a deep learning approach to reduce the computational overhead of collision avoidance, which takes up the largest amount. This is our system flow. From the 6DOF command, we generate IK candidates like the figure B. Among the candidates, we select the best one through our objective function consisting of collision avoidance and smoothness between joints. The collision costs are predicted by our collision cost prediction network. Finally, our method sequentially synthesizes joint configurations that accurately realize the commands while avoiding collision and achieving smoothness. Now, let me introduce our approach in detail. Our approach generates IK candidates with high feasibility using the property of an optimization-based IK, which obtains a solution dependent on an initial configuration. We maneuver initial configurations using the Gaussian distribution to get diverse solutions close to the current configuration. Since we have to satisfy the joint velocity limits given the short time, we set the standard deviation considering the joint velocity limits. Our objective function to select the best one among generated IK candidates consists of smoothness of joints and collision avoidance terms. The smoothness considers velocity and acceleration between joint configurations. And collision cost is predicted by our collision cost prediction network. Our network quickly estimates a quantitative collision cost using an occupancy grid updated from the sensor data in real time. Our network consists of 2 feature extractor for joint configuration and obstacles, and 1 regression module. To train our network, we construct datasets that consist of 500 random joint configurations in 2,000 different environments. From each environment, we extract occupancy grids from sensor data. And we compute collision costs using signed distance field with simplification of robot lengths. Although using signed distance field can compute collision costs, it is hard to use in dynamic environments due to its construction time. Therefore, we use deep learning to predict collision costs without additional preparations. Our loss function consists of 2 terms. One is MSE loss to close the ground truth value, and the other is ranking loss to improve the ranking accuracy with the ground truth. Since our method selects the best one through our objective function consisting of the 2 terms, predicted ranking is more important. Now, let me show you our experimental results. In this problem, we give 6 DOF commands consecutively using a joystick to move in a straight line. Left one is when there is no dynamic obstacles, and right one is when the cart is moving to the robot. The right video shows synthesizing joint configurations away from an approaching cart. In the next problem, we give commands to trace a square while avoiding the static table in the approaching book. In the right video, we can see that the robot avoids the approaching book while following the command accurately. After the book disappear, joint configurations are consecutively synthesized to avoid the table. Thank you for listening. For the details, you can use our project page through this URL.